Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, today in Chemical Thermodynamics we will be talking about systems of variable compositions part 2. To discuss this topic we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you so much. First of all, I wish very good afternoon to all the viewers, dear friends. As you are aware, in our previous session, in our previous lecture, we had covered a brief discussion about what are partial molar quantities, and with special reference to partial molar volume, we had envisaged, by virtue of envisaging different kind of examples, we tried to see what way the volume occupied by 1 mole of a chemical species in a mixture gets different from volume occupied by 1 mole of chemical species when it is present as pure substance. So, on that note, following that discussion, it is now time to discuss other partial molar properties. So, today let us first of all, before we switch on our attention to such properties, let us now discuss one more aspect of partial molar volume, and that is, suppose now for example if we take a huge quantity of water, that is, you can say a room full of water. In that much quantity of water, if you remember, if when we had added 1 mole of ethanol, it did occupy 18 centimeter cube. That is, it raised the volume of the whole content by 18 centimeter cube. However, when in a room full of ethanol content 1 mole of water was added, then it raised the volume to only about 14 centimeter cube. And now it means what we are trying to say is that water 1 mole when added to ethanol, a room full of ethanol content, its volume gets raised only by about 14 centimeter cube. Although the volume gets raised, but now question arises, now imagine a situation when we have a room full of water. Now when we try to add in this whole room full of water content nothing but is magnesium sulfate, 1 mole of magnesium sulfate is being added. What we try to observe there? We try to observe that the volume of the total system, that is the room full of water content, gets decreased by 1.4 centimeter cube for every 1 mole addition of magnesium sulfate. What it does mean? It does mean that we have added magnesium sulfate in the system in a room full of water content, but what has happened is volume has decreased now. What it means? It means that now the partial molar volume can assume a negative value. That is what we are trying to say, that when we add 1 mole of magnesium sulfate to a room full of water, what way the volume of this whole content changes. Now we have observed the volume of the whole content gets decreased. It certainly means that due to addition of 1 mole of magnesium sulfate, there has been a decrease in volume of the system. So it means we can say that partial molar volume of magnesium sulfate would then assume a negative quantity. So that is another basic difference between the molar quantities and partial molar quantities, that for example partial molar volume and molar volume, when we compare, that molar volume will of any chemical species pertains to that volume occupied by 1 mole of chemical species when it is present in a pure as pure substance. But when it is present in a mixture along with several other contents, then we will call it partial molar volume, and the molar volume will always be a positive quantity. This has been tested experimentally, but the fact of matter, by virtue of exemplification of this example of addition of magnesium sulfate, we come to know that partial molar volume can assume a positive value or can also assume a negative value, or it may also lead to an increase in volume. So that is what has been there. So it means partial molar volume can be a positive quantity or can also be a negative quantity, but molar volume will always be a positive quantity. That is what I wanted to convey regarding the comparison between molar volume and partial molar volume. Now, let us switch on our attention towards other partial molar quantities, such as the one we started with, that is nothing but is partial molar Gibbs free energy. Partial molar Gibbs free energy, if you see carefully on this presentation, it is del G, the change in Gibbs free energy or the increase in Gibbs free energy due to addition of D and I moles of component I, keeping the temperature, pressure and number of moles of all other chemical constituent Nj constant, where Nj not equal to Ni. So, therefore, this is how we defined the partial molar Gibbs free energy, and we said that as you are already aware that during our discussion in criteria of spontaneity and equilibrium topic pattern, we introduced a term called chemical potential for molar Gibbs free energy of system. So, here in a mixture, it is not the molar Gibbs free energy which will be the prevailing term, but will be the partial molar Gibbs free energy, and that will be the chemical potential of that particular component which is when present in a mixture of containing various components. Now, this chemical potential is an intensive quantity. Why this is an intensive quantity? You please try to see it very carefully, that it is ratio of change in two extensive properties, that is the Gibbs free energy and number of moles. So, therefore, when is ratio of two extensive properties, so therefore it will be an intensive property. So, chemical potential is always an intensive property of the system. Now, when the question would emerge in the mind of students that when it is an intensive property, then how it will vary with number of moles of other components to it. When it is kept constant, the composition will remain constant. How come? Now, in order to understand this, we must understand that we had made use of the definition of partial molar quantity, that a very small amount D and I of component I to be added, so that composition almost remains constant of the overall system, and that is then the increase in Gibbs energy due to that addition of infinitesimal quantity of number of mole of component I will then be the partial molar Gibbs free energy, and that will be the chemical potential. So, therefore, it is very clear that the chemical potential is an intensive property and is independent of the composition, irrespective of the fact that it is being defined in a way that it is the increase in Gibbs energy due to addition of very infinitesimal number of moles of component I. Infinitesimal means composition remain constant, that is what is being tried to said. So, today we also learnt here about chemical potential. Chemical potential of any chemical species in a mixture is nothing but partial molar Gibbs free energy. It is partial molar Gibbs free energy, and here the chemical potential mu I is given as the symbol for chemical potential, which means the chemical potential for component I in a mixture where there are a number of components which are present. So, it is for the component I, right. Now, this chemical potential is a very central concept in chemistry, and which we will go to see very shortly what it actually means to us. But for the time being, this is what the chemical potential we have tried to define in terms of increase in Gibbs free energy, or in other words we can say partial molar Gibbs free energy. So, now question arises, since other thermodynamic properties like extensive state properties such as enthalpy, entropy, Gibbs free energy, Helmholtz free energy, internal energy, enthalpy, all such do increase in this infinite with number of moles of any one of the components. So, will the chemical potential value can also be defined in terms of other thermodynamic properties? So, answer to this question is of course we can do that. If you want to do that, now let us now see first of all what way we can determine chemical potential, in other words what way we can define chemical potential in terms of change in Helmholtz free energy. So, it is very clear when we are talking about Helmholtz free energy that the state variables to be kept, the constant will be different from that of when we discuss about Gibbs free energy, and therefore prevailing condition within the system will also be different. So, for this purpose if we want to determine chemical potential or define chemical potential in terms of change in Helmholtz free energy, let us consider an equation, that is dG equal to minus SdT plus VdP plus summation mu I dNi. This is the one important equation, one of the fundamental equation for a system having for which the composition may vary as a result of some process during its change in state of system. So therefore, with this consideration of equation, let us now consider what is G. By definition, G equal to the enthalpy minus product of temperature times the entropy. So we make use of this definition of Gibbs free energy G equal to H minus Ts, when in this equation we try to put H equal to U plus PV. By definition, enthalpy equal to sum of internal energy plus the product of pressure and volume of the system. So therefore, those such this equation is also been put in this equation, and therefore ultimately what we get is G equal to U plus PV minus Ts. Now we can rearrange this equation in a way that we can bring Ts term to the first to the second term and PV becomes the third term, and we rearrange and keep in bracket. So what we get, G equal to U minus Ts plus PV. And if you remember, what was U minus Ts? H minus Ts was G, and what was U minus Ts? That was A, Helmholtz free energy. So what we get is the expression inside bracket become Helmholtz free energy is represent Helmholtz free energy function, and therefore there is A plus PV. So A plus PV. So it means G equal to A plus PV. That is what we get an equation. So therefore now we can further rearrange, we can take this PV to the left hand side. What we get is this A Helmholtz free energy equal to G Gibbs free energy minus PV, product of pressure and volume of system. Right. Having said this, now we can differentiate this equation. This is this equation 2. This equation 2 is equation of Helmholtz free energy, which is being defined in terms of Gibbs free energy function and product of pressure and volume being two state functions. Now we can differentiate equation 2. What we get, dA equal to dG minus PdV minus VdP. Why so two terms? Because we are applying here product rule, and we are differentiating first the volume keeping pressure constant, and then we are differentiating volume then we are differentiating pressure and while we keep the volume of the system constant, and therefore we get dA equal to dG minus PdV minus VdP. Right. Having said this, now we make use of equation 1 in equation 3. Why we are saying this? Because equation 1 represent basically the expression for change in Gibbs free energy, dG equal to minus SdT plus VdP plus summation mu I dNi. So we will put the expression right hand side of the expression equation 1 for dG value in equation 3. So now here you can see in equation 3 there is dG. So instead dG, in place of dG, what we substitute, minus SdT plus VdP plus summation mu I dNi, and minus PdV and minus VdP term we just carry as the other term. So now which we upon opening the brackets, it is very clear that VdP plus VdP and minus VdP cancel, and what we get dA equal to minus SdT, the first term here, minus PdV, the second term here, and plus summation mu I dNi. So equation 4 therefore become another fundamental equation of thermodynamics for systems of variable composition. If you remember, in both these equations which we have derived now, the two fundamental equation in terms of dG and dA, it is very clear that the summation terms mu I dNi are extra, and when we compare such equations compared to only single component or constant composition systems. So alright, so similarly we can make use of this equation in order to determine the chemical potential, because mu I is chemical potential. It is very interesting, and it is very important to note what way we can determine chemical potential in terms of change in Helmholtz free energy. So you see in this equation 4, we can see very easily that dA equal to minus SdT minus VdP, plus there are a number of terms which have mu I dNi. For example, mu1 dN1, mu2 dN2, mu3 dN3, mu2 mu4 dN4, and so on and so forth. If we keep temperature, pressure and J's means number of moles of all the chemical constituents means J's. except one of the chemical constituent which we name as I constant. So, what it does mean, temperature constant means in equation number 4 dt becomes 0. So, minus SDT term becomes 0. When volume become constant, then second term minus PdV also becomes 0. And now summation which include a number of terms, all the terms will be 0 except one, which means mu I dni. So, it is very clear, I have written dA under condition of constant temperature, volume and J's number of moles of all the chemical constituents except component I equal to mu I dni. Now, we can rearrange equation 5 in a way that we can divide the equation 5 by dni. What we get, delta A by delta ni under condition of constant temperature, volume and J's I naught equal to J equal to right hand side mu I, chemical potential of component I. So, we can now define chemical potential of component I in terms of Helmholtz free energy as increase in Helmholtz free energy due to addition of negligible amount of component I dni under condition of constant temperature, volume and NJs, that is number of moles of all other chemical constituents except component I constant. That is how we can we have just defined the chemical potential in terms of change in Helmholtz free energy. So, now let us talk about chemical potential in terms of enthalpy change. Similarly, we can consider here the equation, again equation number 1 same, the dg, the change in Gibbs free energy equal to minus SDT plus VdP plus summation mu I dni. Now, since G equal to H minus Ts, so H equal to G plus Ts, which we can rearrange just Ts to, we can take to left side. So, what you get, H equal to G plus Ts, equation 7. Now, when you differentiate equation 7, what you ultimately get is dH equal to dg plus TdS, because the second term is Ts, plus TdS plus SDT. So, now you can make use of equation 1 in equation 8, because in equation 8 you can very easily see that dg is equal to minus SDT plus VdP plus summation mu I dni. So, when we substitute this in equation 8, what we ultimately get is finally dH equal to TdS plus VdP plus summation mu I dni. Now, we can make use of this equation 10 in a way that when we say that if we keep entropy of the system constant, pressure of the system constant and also number of moles of all other chemical constituents except component I, then what it does mean, this equation 10 transform to equation 11, which is dH under condition of constant S, P and J's, that is TdS becomes 0, VdP becomes 0 and dnj's all become 0 except dni. So, therefore, equal to mu I dni. Now, we can rearrange this equation, and what we get ultimately is when we divide this equation with dni, what we get, delta H by delta ni at under condition of constant entropy, pressure and number of moles of all other chemical constituents except component I. Now, this become equal to chemical potential. Now, similarly, we can finally look for definition of chemical potential in terms of change in now this time of internal energy. Let us now talk again about the same equation, dg equal to minus SDT plus VdP plus summation mu I dni. Now, we know that H equal to U plus PV. So, U equal to H minus PV. So, now this equation 13, we can differentiate equation 13 and ultimately what we are going to get is du equal to dH minus PdV minus VdP. Now, this equation 14 basically relate the internal energy change with change in enthalpy and the volume and pressure. So, now we can make use of equation 10 in equation 14. What was equation 10? Was basically expression for dH. If you see it very carefully, dH equal to TdS plus VdP plus summation mu I dni. So, in equation 14, when we substitute for value of dH, what we get is du equal to TdS plus VdP plus summation mu I dni. All these terms, these first three terms which you can see over here in the equation basically equal to dH. So, for dH we substitute the expression and ultimately with VdP term cancel, and what you get, du equal to TdS minus PdV plus summation mu I dNi. So, now in this equation 15, if we keep entropy, volume and Nj's number of moles of all other chemical constituents except component 1, which is which you can say is I, or component number 2 could be I. So, therefore, in the situation all the terms in the equation become 0 except for mu I dNi. So, du equal as under condition of constant entropy, volume, Nj's equal to mu I dNi. Now, we can rearrange this equation 16 in a way that we can divide the equation 16 with dNi. What you get is mu I equal to delta U by delta Ni under condition of constant Sp and J's, which means it is the increase in internal energy with change with when an infinitesimal amount of component I dNi is added to the system, which is so large that this addition has a negligible effect on the composition of the system, constant under condition of constant entropy, pressure, number of moles of all other chemical constituents except component I. With this, we therefore come to the conclusion portions for this different ways of expressing chemical potential. So, you can see here we have 4 different ways now we have studied for expressing chemical potentials. We can express in terms of change in Gibbs free energy, in terms of change in internal energy, in terms of change in Helmholtz free energy, and in terms of change in enthalpy. Now, what is important to note is that it is the change in Gibbs free energy under condition of constant temperature, pressure and J's. It is the change in internal energy under condition of constant entropy, volume and J's. For Helmholtz free energy under condition of constant temperature, volume and J's. And when you express chemical potential in terms of change in enthalpy, it is the condition is that you are required to keep entropy, pressure and J's as constant, because these are the natural independent variables for enthalpy. So, what it does mean, now if you watch it very carefully, only the first one is the one in which we are talking about increase in Gibbs energy with addition of infinitesimal amount of component I, keeping temperature, pressure and J is constant. Now, when temperature and pressure is kept constant, it means we are talking about partial molar quantity. It means although all the 4 expressions are equivalent expressions for expressing chemical potentials of component I in a mixture of defined composition, but the only one which is the one is expressed in terms of increase in Gibbs energy is the only one which can be regarded as partial molar quantity. So, it means that simply to say that chemical potential can be expressed in a number of extensive state variables, but it is only the Gibbs free energy for which the temperature, pressure becomes the natural independent variable and therefore qualifies to be a partial molar quantity. Now, if so, as you had already seen that we can define expression for partial molar quantities also for Helmholtz free energy, Gibbs free energy, internal energy, but what it does mean that for volume we can say VIPM, partial molar volume is increase in volume of system when infinitesimal number of component I is added to the system under condition of constant temperature, pressure and J's, and J not equal to I. So, similarly we can talk about enthalpy, internal energy, but it is important to note that although we have written delta H by delta Ni similar to the chemical potential expression, but the constants which were mentioned in chemical potential needs to be Sp and J's, which are natural independent variable, but when you define partial molar enthalpy, the constants are required to be Tp and J's, not Sp and J's. So, if you can watch it very carefully, all these are partial molar volume, partial molar enthalpy, partial molar internal energy, partial molar entropy, partial molar Helmholtz free energy and partial molar Gibbs free energy. In all of these, the subscripts are all same. It means the the variables which are being kept while determining the change in these different thermodynamic properties, they are being the same. It means the temperature and pressure along with number of moles of all other chemical constituents, that is being kept constant. So, it means that although we have seen in this presentation here all the quantities which are shown in yellow over here in the 6 ones, these are 6 different partial molar quantities. All these are partial molar quantities, but they do not represent a chemical potential. It is only the GIPM, partial molar Gibbs free energy, which by definition is chemical potential. So, again let me emphasize, if you write chemical potential in terms of all the variables, it is only the Gibbs free energy, in terms of which chemical potential when is written is a partial molar quantity, or in other words when you write partial molar quantity for all the various thermodynamic functions, then it is only the partial molar Gibbs free energy which actually is a chemical potential. So, for partial molar Gibbs free energy it is both common, it is also a chemical potential as well as a partial molar quantity, right. Partial molar quantities are, now it is time to understand that partial molar quantities are also related in the same manner as the complete quantities are related. When we say this, what it actually means? It means that suppose for example, we are talking about relationship of enthalpy H equal to U plus PV, which is basically a combination function, if you remember it carefully during our discussion of thermodynamics. So, H equal to U plus PV. So, it means when we go to write expression for partial molar enthalpy, it should also be partial molar enthalpy HIPM should be equal to UIPM plus PVIPM. That means it should be a sum of partial molar internal energy plus pressure times partial molar volume. Let us see how we can derive this equation and we can come to the conclusion. So, if we want to do that, what we can do is we can write the expression H equal to U plus PV. We can differentiate it with respect to number of mole of component I, that is, and then keeping the temperature, pressure, Nj is constant. So, this is how equation 21 represent the differentiation of equation 20, and if you notice it very carefully, left hand side represent HIPM, partial molar enthalpy, and the right hand side two terms are there. The first term represent UIPM plus PVIPM. So, it is very clear that the partial molar quantities are also related the same manner the way the complete quantities are related. Same way you can look for A equal to U minus Ts and you can differentiate it with respect to number of mole of component I, keeping temperature, pressure, number of mole of all other chemical constituent constant, and therefore you can also conclude the same aspect from that derivation. Similarly, you can go for GIPM equal to mu I equal to HIPM plus T SIPM. So, with this we come to understand what way the partial molar quantities can be expressed, and they should also be related in the same manner as the complete quantities are related. Thank you very much. Well friends, in this session we are trying to see what way the partial molar quantities, if there are certain relationships of differential coefficients, are they also applicable on partial molar quantities, and we would also try to see what way the various parameters or thermodynamic functions for the mixing process can be calculated. So let us switch on our discussion to first of all looking for analogy for differential coefficients of various complete quantities. Right. So, if you remember in our earlier discussion of systems of constant composition in thermodynamics section, we had said that rate of change of Gibbs free energy with temperature at constant pressure equal to minus S, that is what we had derived. So, now the question arises, if instead of G is molar Gibbs free energy equal to molar entropy, that is what also we tried to see. Now, the question arises, if this is applicable for molar Gibbs free energy or the complete quantity, the Gibbs free energy, the counterpart in a mixture of a chemical substance is partial molar Gibbs free energy, and which is actually here chemical potential of that particular component, which is mu I. So, delta mu I by delta T at constant P. Now, in addition you can see, if you compare the two expressions over here, and J's also needs to be kept constant. So, now this is equal to minus SIPM. So, this equation should also hold true. What I am trying to say is, when we have already seen just right now that we have given the conclusion that when partial molar quantities are also related in the same manner as the complete quantities. So, this, if that is true, then this relationship must also hold true. Let us see what way we can derive it. Let us take the left hand side of this equation 26, del mu I by del T at constant P and J's. Now, what is mu I? If we substitute for mu I the expression of GIPM, that is partial molar Gibbs free energy. So, what do you get? Del by del T is the same expression of left hand side. Instead mu I you can write del G by del Ni at constant temperature, pressure and J's, number of moles of all other chemical constituents except component I. Now, replace the brackets for the complete differential, like that one of the left hand side, and then now you can keep pressure and J's and I's constant like is over here. So, what it does mean, now you can look for, it means that this is just the partial differential coefficient del mu I by del T is basically a double differential of Gibbs free energy of system. And now it is important to note that Gibbs free energy of a system is a state function, and according to the Euler reciprocity relationship, when you are talking about a state function and you are trying to differentiate it with respect to two different variables or two different parameters, then its order of differentiation is immaterial. That is that holds true for state functions. So, since Gibbs free energy is basically a state function, so here also it will also hold true. When it is so, it means the order of differentiation becomes immaterial, and in that situation we can say del by del T, del G by del Ni, which we had written, the order of differentiation was first differentiate the Gibbs free energy with respect to number of mole of component I, and then whatever the result you get, again differentiated with respect to temperature. Now, you can interchange the order of differentiation. Let us see how we go to do that. So, del mu I by del T at constant P and J is equal to del by del T, del G by del Ni. Now, if you want to interchange the order of differentiation, it means this del Ni we have to write it over here, and this del T we have to write it inside this inner bracket. And not only this, the conditions under which the two differentials were considered, they also required to be replaced. So, here these subscripts should be replaced with outer ones, and outer subscript should replace the inner ones. So, what it does mean, what we try to get is del mu I by del T at constant P and J is equal to del by del Ni times del G by del T under condition of constant pressure Ni's, and overall the kept condition being kept constant is temperature, pressure, Nj's. So, ultimately what you get is del mu I by del T P Nj is equal to del by del Ni instead of this differential del G by del T, which we all know that under condition of constant pressure and Ni's means the composition of overall system constant. So, it is basically is minus S. So, we can substitute for minus S and ultimately we can take minus sign outside, and therefore, we can write del S by del Ni constant Tp Nj is equal to. Now, it is very easy and important to understand, very easy to figure out that del S, the increase in entropy attended by an increase in infinitesimal amount of component I del Ni under condition of temperature, pressure, number of moles of all other chemical constituents except component I, that is Nj's being kept constant, is basically nothing but molar partial molar entropy with respect to component I, SIPM. So, minus sign has been there. So, ultimately that is how we have derived this relationship. Now, we try to look for another relationship to be derived. You see over here, del G by del P at constant T equal to V, we all know this relationship holds true. Now, the question arises, same way does this relationship del mu I by del P at constant T and J is equal to VIPM will also hold true? The same, it can also be derived in the same manner as we had just derived the previous one, except the fact is instead of temperature, now we are dealing with pressure. How the molar Gibbs free energy, or in other words partial molar Gibbs free energy of a component varies with pressure, that is what we need to look at. So, basically we can just retain the left hand side of equation 28 which we need to derive, that is del mu I del P at constant T and I's, this should be equal to VIPM, that is what we are required to derive. If in order to do that, let us start with left hand side del mu I by del P at constant T and I's, which is equal to, now you can see del by del P we have just retained, keeping temperature Ni is constant, this outer subscript remains same, and instead of mu I we have just written this expression for GIPM, because mu I we can make use of mu I in terms of GIPM, and GIPM that is del G by del Ni at constant T, P and J's. Now, in this equation you see the order of differentiation is, we have differentiated the Gibbs free energy first with respect to number of mole of component I and then with pressure. So, we can reverse the order. If we do that, we also need to interchange the subscripts, inner from outer and outer with inner. That is what we can do. Here del P outside and del Ni inside, this can be taken out dNi, and del P can be taken inside like is here, and so also the subscript is being exchanged, the inner with outer and outer with inner. The reason being that this we can do only because of Gibbs free energy is state function, and for state function if it needs to be differentiated with respect to two different variables, the order of differentiation is immaterial and the two remain same. So, with this change, so ultimately del by del Ni with del G by del P at T and I's. So, this expression inside one basically is nothing but Ni is constant, means number of moles of all the chemical constituents constant, means we are dealing with constant composition. For constant composition system, del G by del P at constant T basically is V. So, V we have written, and so you can differentiate V volume of system with respect to Ni under condition of constant temperature, pressure and J's, that is the increase in volume attended by an increase in infinitesimal number of mole of component I under condition of constant temperature, pressure and Nj's, number of mole of all other chemical constituent except component I being constant. So, what it is? It is VIPM, the partial molar volume of component I. So, what I wanted to convey is that if suppose some differential coefficient relationships are there, so analogous to them there would also be some relationship in which partial molar quantities are to be placed. That is what is the conclusion from this observation, right. Having said this, now it is time to understand one more aspect about chemical potential. Chemical potential is also been according to G.N. Lewis, he has coined another term for chemical potential, that is escaping tendency of a substance. basically if on what basis he tried to conclude this term, he coined this term. If we want to understand this, let us take a little observation over here. Let us consider a system. So, let us consider there are two regions in the system. The left side I have represented with region alpha, the right one with region beta. It is just the symbol just to show the right side represented by region beta, the left side represent region alpha. So, now suppose we say that chemical potential by virtue of any of the temperature, the pressure or the composition is been different in the two regions. That is, the chemical potential in region alpha is mu alpha, and chemical potential in region beta we can say mu beta. Now, the fact of matter is that suppose we say that the chemical potential in the two different regions are different, although the same substance is present in both the regions. Then now it is important to understand that it is the temperature pressure being kept constant. Under such condition, if we carry out a transfer of substance, that is dN, infinitesimal number of moles of the substance dN is being transferred from region alpha to region beta. If we do so, then there will be, of course, it means it will lead to some change in state of system. When is so, then there will be change in Gibbs free energy of the system in a whole. If you want to quantify the total change in Gibbs free energy of the system, then let us first of all try to calculate Gibbs free energy change in both the regions alpha and beta and sum them up. Basically, if temperature pressure is kept constant, so dG alpha equal to mu alpha into dN. Now, in region alpha, since the transfer of substance is from region alpha to region beta, it means the dN should be given negative sign. So, for dG alpha, the change in Gibbs free energy of region alpha equal to chemical potential of in region alpha of the substance multiplied by change in number of moles. So, dN we have just given a positive quantity, so minus sign is introduced just to show, just to say that that substance is transferred from region alpha to region beta. So, dG beta therefore is mu beta into dN, that is plus sign. Now, when we have determined the value of these two expressions, and now it is important to understand from where we have got these values, these expressions. Basically, this we have got from the definition of chemical potential. What was definition of chemical potential? This was definition of chemical potential. Mu I equal to del G by del Ni at constant Tp and J's. All we need to do is multiply dNi, which is in the denominator of right hand side, take it to left side. So, what it become? Mu I dNi equal to dG. That is what we have written under condition of constant temperature, pressure and number of moles of all other chemical constituents being kept constant. So, dG equal to mu I dNi, that is what we have written over here. Since there is only one component, so I we have not used the subscript. So, what we have tried to do is making use of the definition of chemical potential, we have tried to calculate the change in Gibbs free energy in the two region, and now the sum of this change in Gibbs free energy of two region basically is the total change in Gibbs free energy of the substance in the whole system. So, dG equal to dG alpha plus dG beta is mu alpha into minus dN plus mu beta into plus dN. So, dN you can now take common. So, minus mu alpha plus mu beta. So, basically now if we say that this mu alpha is greater than mu beta in magnitude, what it does mean? Then mu alpha if is greater has with negative sign, it means in the bracket term is a negative quantity. Now, dN we have just said this positive quantity, then dG is negative because it is a multiplication of one negative quantity in the bracket times the change in number of mole, the transfer magnitude of amount transferred. So, therefore, dG is negative quantity and hence above transfer of substance from region alpha to beta occurs spontaneously. Now it is important to note what assumption we had made. We had said in this conclusion of spontaneity that chemical potential of substance in phase region alpha is greater than chemical potential of substance in region beta, that is mu alpha greater than mu beta. It therefore means a substance migrate or flows spontaneously from a region of higher chemical potential to a region of lower chemical potential. That is what it means. And now you can visualize that if we say that a substance flows from a region of higher chemical potential to a region of lower chemical potential, so what we should call is this chemical potential? It will be a measure of the tendency of substance to escape. So what it does mean? Cannot we call it escaping tendency? Using this argument, G. and Lewis had proposed the term escaping tendency for the chemical potential of a substance. Right. Having said this, now let us try to observe the chemical potential of an ideal gas at a given temperature. If you remember, when we had discussed the topic matter of criteria of spontaneity and equilibrium, we had discussed finally when we have defined that chemical potential of a substance is given as symbol mu, and for a gaseous system, in particular ideal gas, the chemical potential of an ideal gas at temperature P and pressure P is related to its pressure by virtue of this equation, that is equation 32, that is mu standard at. Now if you please notice, mu standard in bracket parenthesis T is been written. This is just to show that standard chemical potential is a function of temperature only, and you could see on the left hand side mu, the chemical potential is written, which is a function of temperature and pressure both, plus RT ln P by P naught. Now in this expression, what is important to note is that whenever we go to take logarithm of a quantity, that quantity should be a dimensionless quantity, and therefore it is pressure of the gas been divided by standard pressure. So the pressure of the gas when is mentioned in bar unit, so then it will equate, and it means the pressure can be expressed in any unit. For example, you can mention it in bar, atmosphere, millimeter Hg. Ultimately the conversion factor will take into account, and when you have divided it with bar, so ultimately it will be a dimensionless quantity. So now let us define what is mu standard also. Mu standard is the standard chemical potential, when the standard means any value, any thermodynamic property under condition of 1 bar pressure, means chemical potential when the pressure of gas is 1 bar or P standard, that is standard chemical potential. So mu Tp equal to mu standard T plus RT ln P by P naught. Now at a given temperature, now you can see very easily, now at a given temperature pressure of the gas is therefore a measure of its chemical potential. Why so? When you increase pressure, what will go to happen? This term, the second term will go to increase. It means the chemical potential is a measure, pressure is a measure of chemical potential. As you increase pressure, the chemical potential increases. So when you specify the value of chemical potential at specified temperature, it means you know its standard temperature, standard chemical potential value, and just you need to do is you just need to know what is the pressure and how much value you need to bring it to that particular pressure, and you can determine its chemical potential. Now the gas we have seen flows from a region of higher chemical potential to a region of lower chemical potential, but we have already seen over here that chemical potential is directly related to the pressure of the gas. It increases with increase in pressure. So it means a region which is associated with the higher chemical potential, it could also be associated with higher pressure, and a lower chemical potential region could be envisaged as if is associated with lower pressure. So therefore we can conclude from this observation that since the gas flows from a higher chemical potential region to a region of lower chemical potential, we can also conclude that the gas flows from a region of higher pressure to a region of lower pressure. So it straight away means the composition of the whole region should be constant. Till the point of time the composition does not remain constant, constantly the flow will continue to occur. Till the point of time the composition becomes constant altogether. That is virtually does not happen. If you would have noticed, if you bring a hollow glass, maybe of steel glass, stainless steel glass or any other glass to your ear, it produces some sound. Basically what it is an indicator of, basically the constant motion of gas molecules or atoms or molecules, whatever is present in atmosphere. For example, nitrogen has been there, hydrogen has been there, oxygen has been there, argon has been there. So all of them which are been there, they are basically constantly set in motion, and there has been constantly migrations from one region to other, because there has been constantly disproportionation from the equilibrium composition in various regions and ultimately reach to same composition, then variation, then reaching to same composition. It continuously, the flow of gas molecules continuously occurs. That has also been chaotic motion, which is at higher temperature it will excite its chaotic motion. Alright, having said this, now it is time to understand what way the chemical potential of a gas gets varied when it goes to a mixture. Till the point of time what we had discussed is just a couple of minutes from now, a couple of minutes ago, what we had discussed it, what way the chemical potential of a pure gas is, how is related to pressure, how is related to temperature, and what it actually means. Now we need to see what way the chemical potential of a gas will be different from the one that of a pure component. If you want to do that, now you see, if we take the same expression 32, which indicate left hand side chemical potential of a gas under condition of temperature, pressure equal to standard chemical potential plus RTL and P by P naught. Now when a gas is a pure gas, so P is the total pressure of the gas and mu is its chemical potential in the pure state. Now if you consider the gas in a mixture, so it will be an ith gas, because there are a number of gases, I equal to 1, I equal to 2. So let's say it could be an ith gas, and then its pressure is equal to its partial pressure rather than total pressure, which you are required to substitute. With this, the expression for chemical potential of an ideal gas in a mixture of ideal gases is mu I mix, that is chemical potential of an ith gas in a mixture of ideal gases under condition of temperature. This is a function of temperature and pressure. In parenthesis, when I have written T and P, it indicates, it shows this is a function of temperature and pressure. This is not a multiplication of temperature comma pressure, please do not confuse with that. It is just to show in the parenthesis term, just to show that this chemical potential of ith component in a mixture is a function of temperature and pressure, is equal to its standard chemical potential of ith gas under condition of constant temperature. Now plus RT Ln, instead of P, just you can note, you may please note that I have written partial pressure of the gas, because there will be some total pressure of the gases mixture, and inside gases mixture, since ith gas is just one gas, so it will exhibit, it will show its own partial pressure. And that partial pressure basically is nothing but, according to Dalton's law, we can take the ratio of partial pressure to total pressure equal to amount fraction. So Pi equal to XIP. So all we can do is we can substitute the expression Pi equal to XIP, equation 34, in equation 33. What we get, mu I mix, temperature T, pressure P equal to mu I standard T plus RT Ln. Instead of Pi, we have just written XIP by P standard. So mu I mix Tp equal to mu I standard T plus RT Ln. Now it is like log of A into B equal to log of A plus log of B. So RT being common multiplication factor for both, so RT Ln P by P naught, P by P standard plus RT Ln Xi. Now it is important to note, if you remember it, it is the ith gas. it could be present in pure state or in a mixture, its standard potential will be, chemical potential will be the same value, mu I standard T plus RT ln P by P naught, P standard. P is total pressure. So it means when the pressure of that particular gas, when it is present as pure substance, then it means the first two terms, sum of first two term indicate what? It basically indicate that chemical potential of that ith gas. If you please note it very carefully, I have put a asterisk over there as superscript. It means it is chemical potential of ith gas when it is present as pure substance equal to its chemical potential under standard condition at which is a function of temperature plus RT ln P by P naught. So in this equation, the sum of two term represent mu I star, which is a function of temperature and pressure, equal to mu I mix, which is again a function of temperature pressure. Now in this right hand side, we also need to add another term RT ln Xi. Now this mu I star Tp equal to mu I standard, which is a function of temperature, plus RT ln P by P standard. Now since for a mixture, if you consider a mixture, if suppose 1 mole of gas 1, 2 mole of gas 2, 3 mole of gas 3 and so on and so forth has been added, it straight away means that since all the number of moles are being added of various gases, the number of mole of any particular gas divided by total number of moles of all the gases will always be a fraction whose value will always be less than 1. So when this is so, it means Xi will always be less than 1. So with taking such value, it straight away show that second term RT ln Xi in the expression of mu I mix equal to mu I mix Tp equal to mu I star Tp plus RT ln Xi. Here Xi is always less than 1. So therefore log of anything less than 1 is always a negative quantity. So it means RT ln Xi is a negative quantity. So it is something like from the chemical potential of a gas under temperature T at pressure P, from which RT ln Xi factor once gets subtracted, basically therefore this is equal to mu I mix. It straight away shows that mu I mix, chemical potential of a gas in a mixture at same temperature and pressure, is always less than chemical potential of that gas when it is present as in only pure state. So with this, with the conceptualization and expression being derived for chemical potential of a particular gas in a mixture, now we will try to see what way the mixing process occurs, and we will try to calculate Gibbs free energy, enthalpy, volume and entropy for the mixing process for mixing of ideal gases. That will be taken up in the next session. Thank you so much.
On that note, I would like to thank sir for this very enriching discussion, and I would like to thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.